Assalamualaikum, we are from group 2 of PHY3902 and we will be explaining about diffraction intensity of multiple slits and grids, which is the 7th experiment in our syllabus. Our group members are Nasuha binti Amal Baiz 229031, Tia Mukhalisa Wafin 229525, and Nurhusna Maisara 231471.
Assalamualaikum and hi, my name is Nurhusna Maisara, metric number 231471, and I will be talking about the introduction, theory, and experimental setup of this video presentation. So for the principle, multiple slits which all have the same width and the same distance among each other, as well as transmission grids with different grid constants, are submitted to laser light. The corresponding diffraction patterns are measured according to their position and intensity by means of a photodiode which can be shifted. Theoretically, if monochromatic light of wavelength impinges on a system of parallel and equidistant slits, the following will be true for the light intensity I of beams reflected by an angle, where the intensity as a function of phi, denoted as I times phi, is proportional to b squared and is expressed as the product of three terms. The first term is the sine squared of the fraction pi over lambda times b times the sine of phi, divided by the square of the same fraction, pi over lambda times b times the sine of phi. The second term is the sine squared of pi over lambda times g times the sine of phi. The third term is the reciprocal of the sine squared of pi over lambda times g times the sine of phi, where b is the width of slit, g is the distance between slits, and p is the number of slits. According to Fraunhofer, the minima and the peaks of a single slit are called first-class interference, whereas the interaction of several slits yields second-class interference. Observing only a single slit, which is the first factor, this yields a minimum intensity when the numerator becomes 0. In this case, the following is valid, where sine phi k is equal to k times lambda over by b, where k is 1, 2, 3, and so on and so forth. And the angular position of the first-class peaks is given approximately through sine phi k is equal to k plus 1 over 2 times lambda divided by b, where k is again 1, 2, 3, so on and so forth. If several slits add together, the minima of the single slits always remain. Supplementary second-class minima appear when the second factor also becomes 0. For a double slit, where p equals to 2, the 0 points can be easily calculated by simple transformation of the second factor. Equation 1 then yields 4 cos squared of pi over lambda times phi equals 2 plus minus 1. This expression becomes 0 for sine phi of h equals to 2h plus 1 divided by 2 times lambda over g, where h is 0, 1, 2, 3. The following is valid for the intensity I of the main second-class peaks, where I is directly proportional to p squared. The main second-class peaks thus become more prominent as the number of slits increases. There still are p minus 2 secondary second-class peaks between the main peaks. When light is diffracted through transmission grids with lattice constant g, the diffraction angle of the main peaks fulfills the following relation: sine phi k equals k times lambda divided by g, where k is 0, 1, 2, 3. Experimental setup to investigate the diffraction intensity of multiple slits and grids can be seen in Figure 1. Positions of the components on the optical bench: laser is equal to 2.5 cm, f over 20 mm lens is equal to 14.5 cm, f over 100 mm lens equal to 27.5 mm, diffracting objects equals to 33 cm, slight mount lateral adjustment, the caliber is 147.5 cm.
This table appears to present data related to diffraction experiment with measurement for diffraction intensity and corresponding position in millimeters for 3 different slits with b equals to 0.1, b equals to 0.2, and b equal to 0.4. The table likely corresponds to experimental measurement of light diffraction through single or multiple slits. The position indicates the spatial location on the screen where diffraction intensity is measured, with x equal to 0 in the central maximum. The diffraction intensity varies depending on the position. Peaks and troughs in intensity likely correspond to the maximum and minimum of the diffraction pattern. For narrow slit b equals to 0.1, the diffraction intensity value are lower and the spread of position, however, is smaller. As the slit with increase b equals to 0.2 and b equals to 0.4, the diffraction intensity value increase and the spread in position becomes broader. This reflects the relationship between slit width and the diffraction angle. This table, labeled as table 2, appears to describe diffraction pattern under the different conditions for slit width, slit pressure, and number of slits. Each setup includes two sets of measurement, one for negative positive, x less than 0, showing diffraction intensity value symmetrically decreasing as position become more negative. Another for positive position, x more than 0, showing diffraction intensity increase symmetrically as position becomes more positive. Data is symmetric around x equal to 0 is aligned with the theoretical prediction. The diffraction patterns are symmetric in respect to the central maximum. This table labeled as table 3 seems to explore relationship between the lattice constant in millimeters and the reciprocal distance in millimeters for three different values of k, likely representing it as experimental or theoretical parameters. Lattice constant. The lattice constant represents the distance between points in a periodic structure, such as the crystal lattice or diffraction gradient. Value of t are consistent across k equals to 1, k equals to 2, k equals to 3. The parameter k influences d. As k increase from the 1 to 3, the value of d increase for the same g. This suggests the d might depend on both t and k as a proportionality constant for scaling factor.
So for these discussions, the data compress diffraction intensity as a function of the position x for the different slit width, which means they have the 0.1 mm, 0.2 mm, and 0.4 mm in a single slit diffraction experiment. So these broad central maximums align with the theoretical predictions that narrower slit lead to the wider diffraction pattern due to the inverse relationship between the slit width and the angular spreads. So as the slit width increases, the intensity at the central maximum rises, and the width of the central peak decreases, indicating a tighter conformance of the lights. So the slight loops, which means secondary maxima, become more distinct as the slit width increases, highlighting the sharper central peak and the relative permanence of the higher order fringes. So in the table 2, the data show the diffraction intensity I as the function of the position x for the slit width 0.1 mm, rating spacing 0.25 mm, and the diffraction order, which means n1, n3, and n4, illustrating how the diffraction order affects intensity distributions. So overall, the data confirm the theoretical relationship between the diffraction order, energy distributions, and also the intensity patterns. And with the lower order producing broader and the less sharp peaks and higher order creating a narrower, more defined fringes. So the data present the relationship between the lattice constants and the reciprocal distance for the different values of k, which means I have k1, k2, and also for the k3. So the reciprocal distance increase with both the value of the k and the decrease of the lattice constant, reflecting the inverse relationships between the lattice spacing and the reciprocal distance, indicating tighter reciprocal spacings. The observed behavior is consistent with the principles that reciprocal distance is inversely proportional to the lattice constant at the scales with the order of k of the diffractions. So for the conclusions on these experiments is the analysis of diffraction patterns and reciprocal distance highlight the interplay between the physical parameters and such as slit width, grading spacings, lattice constants, and also diffracting order. Narrower slits produce the broader diffraction patterns with the lower peaks intensity, while the slit generates narrower and more
more intense center maxima. The higher diffractions orders, which is ends, result in sharper peaks with the weaker size loops due to the increased energy distributions across the fringes. Similarly, the reciprocal distance is inversely proportional to the lattice constants and the scale with the diffractions of the order k, demonstrating that the larger values of k correspond to the tighter reciprocal spacings.
That's it from our group. Thank you.